Hey guys, Miss Subin here, and today we're going to be talking about the real number system. Now, the real number system is just a way that we categorize numbers in math, so it's a vocabulary thing. But understanding the real number system can also help us understand numbers better as well. So let's go ahead and just jump right in. So let's start with our objectives. Today we will define rational and irrational in order to categorize values in the real number system. Now, there are a lot of categories to the real number system, but this year and today, we're just focusing on rational versus irrational. All the numbers that we study this year will fall into one of these two categories. Today, we will practice converting terminating and repeating decimals into fractions in order to identify rational numbers. And then today, we will discover what types of numbers cannot be written as a fraction in order to identify irrational numbers. So before we start, let's make some predictions. We're going to be defining rational and its opposite, irrational. What comes to mind when we say a rational number? I want you to think about vocabulary you know and see if in the word rational you see any words you may know. The word we're looking for is ratio. Rational numbers can be written as a ratio. The most common kind of ratio we talk about is a fraction. A rational number is a value that can be rewritten as a fraction or a ratio. So if it can be written as a fraction, it's a rational number. If it can't be written as a fraction, it's not rational. So let's start with some easier examples. Fractions and mixed numbers. Well, because they're already fractions, they're going to be rational. There is a trick though, because sometimes there might be a fraction, but it has a part that's irrational, and we'll talk about those. But for the most part, if you have a regular fraction, like 1/2, it's rational. 1/2 is already a fraction. If you have 3/4, rational. It's already written as a fraction. You can also have an improper fraction. 7/2. It's rational. It's written as a fraction. There's no trick parts to these questions, especially when there's two whole numbers involved. 1 is a whole number, 2 is a whole number, 3 is a whole number, 4 is a whole number, 7 is a whole number, 2 is a whole number, and so on. And then whole numbers. All whole numbers can be written as a fraction over 1. So for example, 2 is equal to 2 over 1. 7 is equal to 7 over 1. -3 is equal to -3 over 1. If it's a whole number, it's going to be rational. So right away we know that fractions and mixed numbers and whole numbers are all rational, as long as there's not a trick part. But don't worry about those today. So medium examples. Decimal values have to be checked if they can be converted into fractions. We've been talking for the last couple classes about when we can convert or how to convert. Turns out there are some cases where we can't, but let's talk about the ones where we can convert. So there's a couple of different types that can be converted that we've been talking about. So we're going to recall the ones that we've been talking about for the last couple days. Decimal to fraction conversion. Terminating decimals are decimals with a finite number of digits, meaning that there's a definite end. These ones do not repeat. So converting 3.8 into a fraction. So 8 is my numerator, my denominator is 10. I can simplify this by dividing by 2. Then we have to remember to put our whole number on there. So 3 4/5, that's rational, it can be written as a fraction. Even though there's a whole number is also rational, so we're fine. Therefore, terminating decimals are always rational. Then the next day we talked about repeating decimals. These are decimals with an infinite number of digits that repeat. So for example, we have convert 4.36 repeating into a fraction. Well, we know to do that by taking the numbers after the decimal and making that our numerator. Our denominator, we want to use 2 9s because there's 2 digits. If you wanted to use 100, be careful. It's a repeating decimal, so we want to use 99, because it's a little less than 100, so it gives us that remainder that will repeat. Then, of course, we simplify. So both of these can be divided by 3. So 12 over 33. We can actually do that one again by dividing by 3. And I get 4 over 11. Don't forget your whole number. Repeating decimals, they can be converted into a fraction. So therefore, all repeating decimals are always rational. So if it's terminating or if it's repeating, we can say right away, it's a rational number. So we talked about our repeating decimals and we talked about our terminating decimals. Now, think to yourself, what other types of decimal values could there be? So far, we've already talked about terminating and we talked about repeating. So the only type that's left is the opposite of both of those. All that's left is a never-ending and non-repeating decimal value. So for example, we have 3.826405 ... The reason we use that ... is because whoever calculated this number discovered that you cannot just have this go on forever, because we'd have to sit here and write down all the numbers. It doesn't repeat, so we can't just throw a hat on it like we do with our repeating values. And it doesn't end. 5's not the last digit. That ... tells me that 5 is as far as they got before they were either tired of calculating or didn't need to know any more digits. But the ... tells us that there are more digits. They're just not written down. So let's try to write it as a fraction or as a ratio. If we can write it as a ratio, then it's going to be rational. And if we can't write it as a ratio, it's irrational. Irrational means not rational. So let's give it a try. Based on how we write our fractions, I'm going to start by making my numerator the numbers after the decimal. 826,405. Then it's not repeating, so I'm going to use a power of 10. 0, 0, 0, 1, 2, 3, 4, 5, 6. So it ends up being 1,000,000 in the bottom right now. Now this would be great if 5 was our last digit. But 5 is not our last digit. This goes on forever. And we don't know the numbers. And we don't know a lot of information here. So even though we can get really close to writing a fraction, because of these ... this is actually incomplete. We can't write this as a fraction. So never-ending, non-repeating decimal values are irrational. Even though we're smart enough to figure out how to write it, it's just not possible. Now, another value to remember when we're talking about rational versus irrational is our friend pi. Now, some of you may be thinking pi is 3.14, but that's just because when we're doing math, 3.14 gets us close enough to our answer. The true value of pi is 3.1415926535897. It continues on forever and ever and ever. It's an irrational number. Pi represents a never-ending and non-repeating irrational number. In most cases, all of the ones you're going to see today, if pi is in the value, then the whole answer is irrational. There are ways to make trick problems, but I'm not going to do that to you today. So some examples of irrational numbers would be pi. If you just see pi and I ask you if it's rational or not, it's not rational. 5 pi, well, 5 times that crazy number we have over here is still going to be irrational. And lastly, pi divided by 2, pi over 2, that's also going to be irrational because we're taking a never-ending number and dividing by 2. The answer is going to also be never-ending. So if pi is in it, it's irrational. Here's some harder examples. You're going to have to use what you remember about square roots from yesterday. So our perfect squares, we have the square root of 4. So we have to think to ourselves, what times itself equals 4? That'll be 2. That's a perfect square. Then we have to think through, here's a second example. Square root of 100, which is equal to a number times itself that will give us 100, which would be 10, because 10 times 10 is 100. So both of those are perfect squares because we get a whole number answer. Because their solutions are rational, because their solutions are whole numbers, perfect squares under a square root are rational. Perfect squares are rational. Now non-perfect squares, so for example, the square root of 2, no, 1 times 1 equals 1, 2 times 1 is 2, but it's not the same number. This one ends up being a crazy number. I'm going to actually put it in my calculator, so just give me 1 second. So if I put my calculator on 2 and then find the square root, I get 1.1414213 ... That's a never-ending decimal. A never-ending non-repeating decimal, that's going to be irrational. Let's try another one. Square root of 13. If I put 13 in and find the square root, I get 3.6055512. It goes on forever too, and it's not repeating. So this one's going to be irrational as well. If it goes on forever and it doesn't repeat, it's going to be an irrational answer. Because their solutions are never-ending, non-repeating decimals, non-perfect squares, perfect squares under a square root are irrational. So let's just talk about everything that we did because there's a lot of things going on. The goal of today is just to sort numbers. We're not actually manipulating them in any way unless we're trying to prove that something's irrational or if something is rational. So a value is rational when it can be written as a fraction. So starting off as a fraction, it's rational. Starting off as a whole number, it's rational. If it's a terminating decimal, we know we can write that as a fraction. That's rational. If it's a repeating decimal, we know how to write that as a fraction, so that's going to be rational. Perfect squares in a square root, that's going to be rational because our answer is a whole number. A value is irrational when it cannot be written as a fraction or as a ratio. So our examples here would be a never-ending, non-repeating decimal. That's going to be the most common. Pi, if you see pi, it's probably irrational unless someone's trying to trick you, which I won't do today. I will warn you before I try to trick you, and it wouldn't be until you guys got good at this. A value being multiplied or divided by pi is also irrational because pi makes the value irrational. And finally, non-perfect squares in a square root. So if you try to take a square root of a number that's not a perfect square, it's going to give you that never-ending, non-repeating decimal, which is already irrational. Hopefully this helps and you'll be able to get through today's activity. Good luck.